Okay, so I wrote the classification theorem up that I had last time, slightly more precise form. I added unital just because I only defined the Elliott invariance in the unital case last time. There is a non-unital version. And it's also true, I didn't state yesterday, not only does this recover the algebras up to isomorphism, but isomorphisms is invariants actually do lift to isomorphisms of the algebra. Okay. So my plan is, I think for today, I just want to talk more generally about how one approaches classification broadly, in particular, the intertwining arguments that underlie most isomorphism theorems in the subject. But before I do that, I do want to come back and say a bit more about Z stability, which I really didn't say anything about last time. I'll start there. This is, and I'll point out that there is this actually is analogous to a von Neumann algebraic property, which appears in the Kahn's classification. This is McDuff's property. And I'll actually start with the von Neumann algebra side of this, which is quite a bit cleaner. But so take unital embeddings of matrix algebras. So M1 by M1 matrices into the N2 by N2 matrices and keep going. Where choose the NKs however you want. I mean, for embeddings to exist, they have to, each has to divide the next. We'll take the indices to go off to infinity. So you think you're taking this, say a 2 by 2 matrix, then you pass the next level, you're dividing it into smaller bits. You get maybe a 4 by 4 matrix, then maybe an 8 by 8 matrix when you divide each into smaller bits. And you can get some kind of fractal like construction, some sort of non-commutative analog of the Cantor sets, if you like. I guess that would be when the nk is 2 to the k. But so if you take the union, there's a natural algebra structure there. You just multiply them whatever, large enough matrix algebra containing both their elements. And there's a natural trace given by, you have a trace on each coordinate, and they'll fit together correctly to give you a trace on this algebra. And if you take the von Neumann algebra completion with respect to this trace, you get a von Neumann algebra called R, the hyperfinite 2-1 factor. It does not depend on how you choose the sequence of embeddings to start with. It's due to Murray and von Neumann. Right. Okay, I think this came up in Jesse's talk on Tuesday as well. I think even defined this way with just powers of 2. But so what McDuff's property is well, there's 2 equivalent conditions. One of them is a tensor product property that so for a separable 2-1 factor, let's say it this way. If you take the tensor product of 2-1 factor M will absorb R under tensor product is equivalent to this following approximation condition, which actually has a very similar form to property gamma that was talked about on Tuesday, where you want a very rich supply of central sequences in this algebra. Well, gamma was there's a sequence of trace zero unitary is approximately central. One way of saying this is actually there's two sequences of trace zero unitaries which are approximately central and don't commute with each other. I'm actually going to put something stronger than that here, so because it fits better with the Z stability. But for any n at least 2, for any finite subset of M, the positive epsilon, so that double subset symbol means finite subset. There's a copy of the n by n matrices inside of M, which almost commutes with my given finite set. So that AXN minus XN, or let's say AX minus XA, 2 norm is below. Let's start this for all A and F, X and Mn. Yeah, so everything in Mn, or if you like, just in the ball of Mn, almost commutes in 2 norm with the, or equivalently in the Stroughton operator topology with the finite set. Okay. That's also equivalent to the existence of an n with that property. If you can do it with n equals 2, then you can do it with any other n. Right. Okay. So this is, well, it's usually in the von Neumann algebra literature called McDuff's property, but I'm going to call it R stability here because Z stability is going to be the exact analog of this, just as to try to keep the notation somewhat consistent. I should mention here, it's R itself is R stable. So there are a lot of these algebras. You can take any 2m factor you want, tensor it with R, and you have something that absorbs R. I don't actually know 2m factor theory well enough to know exactly how restrictive this condition is. There's certainly several 2m factors where it fails. I don't know how. Yeah, it's. What's relevant here, though, is this result of Con if M is a separable injective to 1 factor, then M is R stable. So in the injective case, it's automatic. Well, I think I've been said a few times, the only example of such an injective to 1 factor is R, and R is R stable. That is trivially, I mean, not entirely trivially, but by relatively elementary arguments. But this actually feeds into the proof of Kahn's theorem. So this is a key part in showing M has to be R. That, oh yeah. Between epsilon, F finite subset of M. Yeah, double subset symbol is the, yeah. Just for, that's what I'm using for the finite set, just 2 subsets. Yeah. Yep, no problem. Right. So the point here is, if you compare this with what I had with Kahn's theorem, to start with separable injective factors are classified. The UCT wasn't there in the von Neumann algebra side. That's really no von Neumann algebra analog of that. It's purely topological in nature. There's no Z stability condition on the von Neumann algebra side because it's automatic. Some kind of Z stability is going to be an analog of this. It just happens to not be automatically true in the von Neumann algebra setting. You really need to assume it. But so I gave away the answer here, but the question that would underlie this is what C star algebra should use instead of R. And you could try to take the same algebra, take a increasing sequence of matrix algebras, take their norm closure to get a C star algebra instead of a von Neumann algebra. So you get what are called UHF algebras. So the operator norm closure of that union does depend very much on the sequence of ends you choose. So do depend on the choice of NK vector. I mean, they're, of course, not entirely. You can pass to a subsequence, but no problem. Or you can somehow shuffle around the indices to a certain extent. What they turn out to really depend on is the prime factorizations of the NK. And what you end up with is called the supernatural number. Which is a formal product of primes, not necessarily finite. Right. Okay. So in some sense, any of these could play the role of R, and you somehow want to choose, the correct one. So there, among all these UHF algebras, there is the largest one. Where you take, usually called Q, with the supernatural number. You take every exponent to be infinity. So it's maximal in the sense that all the UHF algebras will embed into it. And by construction, it's also this dense subalgebra of R, and we'll actually share quite a few properties with R. Right. Okay. The problem with this algebra is being Q stable actually becomes a very restrictive condition. So it's Q stable if A tensor Q is A. And tensoring with Q actually has quite a bit of effect on K-theory. The K-theory of A will be the K-theory of A tensored with Q, of course. And that tensor product turns out to be exactly the rationalization of the K-theory. You're tensoring the K-theory group with the rational numbers. Now, if you start with a C-star algebra, say as in the classification theorem, there's no reason to think that the K-theory has this property. I mean, that's a rational vector space. This is probably just some abelian group that you're putting really huge restrictions by demanding Q stability. But if you do this, McDuff's theorem, at least the version for every matrix algebra, Q stability is characterized by McDuff's property and operator norm. The existence, as you start varying the n here, if you took have approximately central copies of the 2x2 matrices, you end up being stable under tensoring with the to infinity UHF algebra. The fact that you could, if you have it for all N, then you're stable under tensoring with all the various UHF algebras. Okay. So the other UHF algebras all have similar problems. If you took the UHF algebra of type 2 infinity, when you tensor with that, you end up tensoring the K theory with the dyadic rationals. Then usually that's going to change what the K theory group is. But it turns out among all possible C-star algebraic analogs of R, there is actually a sort of a minimal choice you can make, which is called the Jane-Sue algebra. Always known by Z. And I'm not going to actually define this algebra, but you can sort of think of it as the intersection of all these UHF algebras, where that MP infinity is the UHF algebra with supernatural number P infinity. I don't know how rigorous you can make that equality. But sort of the way you can think of it as being somehow the smallest of the UHF algebras, even though it's itself not actually UHF. It's infinite dimensional and has no projections. Right. Okay. But it has this property that tensoring with it doesn't change the K theory. In fact, doesn't change the Elliott invariant at all. But if the classification theorem is going to be true, A tensor Z better be isomorphic to A. That's because the Elliott invariants are isomorphic. This is often there's more assumptions in this if you see it in literature. It's because I've chose to remove K0 plus from the invariant. The positive cone in K0 can change when you do this, but okay. So this is what the Z stability condition is. It somehow plays the role of McDuff's property without forcing any K-theoretic restrictions. There is a characterization in terms of essential sequences, which looks a lot like this, except you have to replace matrix algebras with something more complicated to get around the fact that A probably doesn't have any projections. Okay, so that's Z stability then. All right. So the other thing I spend most time on is talk about how do you actually even approach, this sort of classification problem. How do you prove two algebras are isomorphic? Well, one way or another, you have to write down homomorphisms in each direction and show their inverses. And the answer becomes, instead of, to shift your focus off trying to classify the algebras and just fix two algebras, A and B, decide what the morphisms from A to B look like. So classify morphisms is the way one approaches this. I'll explain what I mean by that, but first. So first, if you take two unital C-star algebras, let's say the A is separable. Then and let phi and psi from A to B be morphisms. How high up can I go with this? Is that still good? Okay, okay, that'll work. Okay, so yeah, you have two morphisms from A to B, and I'll say they're approximately unitarily equivalent. So right, phi, all right, tilde sub approx sub u of psi, or approximate unitary equivalence. If there's a sequence of unitaries in the codomain, approximately conjugating one map to the other. Pointwise and norm. I'm assuming algebras are unital just because I don't want to deal with unitizations. You could do a non-unital version. There's the domain. If the domain wasn't separable, you'd probably should use nets, but everything else I'm going to say about this is false in the non-separable setting. Anyway, so I'll just keep it separable. Okay. Right. So that's going to be the right notion of equivalence. So we're going to try to decide classify morphisms up to this notion of equivalence. And the way we want to classify them is in terms of some functor, like we do with the classification of the algebras. So for a functor f from C star algebras to, all right, C, some other category, which is invariant under approximate unitary equivalence. So two equivalent morphisms induce the same map in this target category. And the things to keep in mind are like K-theory, traces, ideals. I mean, well, the Elliott invariant in particular will satisfy this. I'll say that F classifies morphisms from one algebra A to another algebra B if two conditions hold. First is a uniqueness condition that if you have two morphisms from A to B that agree on the invariant, then they're approximately unitarily equivalent. You're supposed to imagine this F is somehow computable, and now you have some computable test to decide when two morphisms are approximately equivalent to each other. The other half is an existence theorem that, or an existence condition. There's not a theorem here, still a definition. If you have some map from A to B at the level of this invariant, it's induced by a homomorphism at the level of C star algebras. So you have a way of systematically building maps and deciding when they're equivalent, assuming you understand whatever the functor is, likely K-theory or something related to K-theory. So a theorem that almost all classification results go through is that classification of morphisms implies the classification of algebras. It's hard to know where to attribute this to. It's certainly implicit in Elliott's work on AF algebras and stuff that happened since. I think Mikkel Roortum is responsible for really systematizing this with his work on Kunst-Krieger algebras. But if, well, let's say if S is a class of C-star algebras, separable, F is this functor as before. So for all A and B and F and S, F classifies morphisms A to B. Then A is isomorphic to B if and only if F of A is isomorphic to F of B. So if you have any functor of any sort, if it describes morphisms between the algebras you care about, then it decides when the algebras are isomorphic. In fact, what you end up proving is a strengthened form of existence, that not only do morphisms lift to morphisms, but isomorphisms lift to isomorphisms. I should admit at this point, I'm kind of suggesting something that's not true. The Elliott invariant does not classify morphisms between that class of algebras. There's extra K-theoretic obstructions. What happens is you end up building some bigger functor, some other functor F, which does classify the morphisms and then show isomorphisms on the Elliott invariant to extend non-canonically to isomorphisms on this larger thing. That, the Elliott invariant is not actually what you apply this theorem to when you prove classification, but yeah. For fixed A and B, yeah. So one A and B at a time, yeah. And here I want to classify all morphisms in every direction between whatever collection of algebras you care about, yeah. Right. So this one I will prove, at least give prove most of this result. So the first part is like just purely algebraic. You fix an isomorphism and we're trying to show, well, F A is isomorphic to B, but moreover that we can choose the isomorphism to induce alpha. So by our existence results, we know we can at least lift alpha to some homomorphism, not necessarily an isomorphism. And I apply it again with the roles of B and A reversed, which I'm allowed to do here. It's, I can lift its inverse as well. So there exists. And there exists a psi naught from B back to A, which realizes alpha inverse. So two applications of the existence portion of the hypotheses. And now the game is to compare the compositions to the identity. And if you look at, say, psi naught, phi naught from A to A, On the functor, that's alpha or alpha inverse alpha, which is the identity. So by the uniqueness applied to maps from A to A, psi naught phi naught is approximately unitarily equivalent to the identity on A. And you can play the same game with the flipping the role of phi and psi. You get the other condition that now if these were equal, then phi naught and psi naught are inverses of each other. So phi naught was an isomorphism. So they're somehow inverses up to approximately unitary equivalence. And the game is to kill that approximate unitary equivalence and replace it with equality. Okay. So now the analytic portion of trying to get rid of the equivalence here. It's usually called Elliott's intertwining argument, or really one of many things called Elliott's intertwining argument. Sometimes it's the two-sided intertwining argument. So what it will, so give more details in a moment, but just the idea behind it. We know psi naught phi naught is approximately unitarily equivalent to the identity on A, which means there's a unitary conjugating the composition close to the identity. So there's some unitary in A, so that if I conjugate by that, I'm close to the identity in the pointwise norm. So when you actually start quantifying this, it's going to be pointwise, these are within epsilon on some prescribed, within some prescribed epsilon, some prescribed finite sets. But that map I'm going to call psi 1. So what you have now is you have your phi naught from A to B. The psi naught went backwards. I conjugated it at least to be close to an inverse or left inverse of phi naught. And then the other next step is going to be now phi naught psi 1 is, I can pull the unitary through, I get phi naught u times phi naught psi naught, which is unitary equivalent to phi naught psi naught, which is then approximately unitarily equivalent to the identity on B. So I can play the same game. There exists some V in the unitary group of B, so that I can conjugate phi naught psi 1 close to the identity on some finite set. That map is then called P1, and it fits in the picture here. Then you iterate. Psi 1, phi 1 is close to the identity on B, but phi 1 psi 1 is far away. You can correct that by conjugating by another unitary. So you get a psi 2 and a phi 2, and so on. Yeah. Oh, that's, you're right. You're right. Psi 1 is add u, psi naught, and then pull the phi past the add. Yeah, sorry. Sort of. Yep. Oh yeah. The question was, where was that coming from? Let me just throw another step in. Was it phi naught psi 1 is phi naught add u psi naught, and then when you pull the add past the phi naughts, it, yeah. Right. Yeah. So you get is this two-side, this is why it's called the two-sided intertwining. You're intertwining these maps between this one. Somehow have these intertwining maps between A and B. And what will happen is if you make careful choices of estimates, the phi ends will form a Cauchy sequence and the psi ends will form a Cauchy sequence. Their limits will be actual inverses of each other. Okay. So a little more detail here. One inductively constructs let's say yeah, so you have increasing sequence of finite subsets of A and of B. The F start at naught, G start at 1. That doesn't really matter. It's just indexing convention. Here. You have maps phi n from A to B and psi n from B back to A, so that they're, okay, let's go over here. The FNs increase to A and the GNs increase to B. Of course, now I'm really using separability because the union of the FNs is countable if the FNs are all finite sets. Psi n plus 1 phi n of A. So psi n plus 1 is almost an inverse to phi n, say less than 2 to the minus n for all A and Fn, and symmetrically with a degree shift. For all B and Gn. Each phi n is unitarily equivalent to phi, and each psi n is unitarily equivalent to psi. And the third one, they map finite sets. Okay, so if you took that last condition, well, you can always arrange if that's why you build these things inductively and just keep enlarging the finite sets at every stage. It's just routine induction to do this. Basically what I wrote there. Then let's just move to our board. What one checks is that with this choice, the phi ends and psi ends are Cauchy. So one shows that phi n of A, n equal 1 to infinity, that some sequence in B is Cauchy for all A. And well, at the first step, you fix one of your finite sets, show it on that finite set. Then, of course, it's true on the union, and hence on the closure, which is by an epsilon over 3 argument. So you have its Cauchy on the whole algebra. So let phi be the pointwise limit. And similarly, psi the limit in the other direction, limit of the other maps. Okay. If you do that, because the phi n and psi n are approximate inverses of each other, and the limit they're actual inverses. So psi phi is the identity on A, phi psi the identity on B. So phi is an isomorphism. Also, by construction, phi is a limit to things unitarily equivalent to phi naught. So phi is unitarily equivalent to phi naught. This f that we were dealing with is a variant in approximate unitary equivalence. So f of phi is f of phi naught, which is right at the top board there, the alpha we were aiming for. So, right. What it somehow does is it shifts the problem from, instead of trying to understand the algebras up to isomorphism, you shift the problem trying to understand the morphisms up to equivalence. Which in practice, and often in practice, it's even the morphism results that are more useful than the algebra isomorphism results in applications. Okay, let me do an example here. So first, so a C-star algebra B has classification of projections, or sorry, classification that's supposed to be cancellation of projections if for any 3 projections in matrices over A, the first two in MK of A and third one in R and ML of A, you want to know that P direct sum R being equivalent to Q direct sum R implies you can cancel R. All AF algebras will satisfy that. Any algebra of stable rank 1, where the invertible elements are dense, will satisfy this. Okay. So the theorem here that got mentioned in some form in Andrea's talk yesterday, if say for unital C star algebras A and B with A, AF, and B with cancellation of projections, the K0 group, this time with its order, so if you have existence and uniqueness results here. So if you have a map from the K theory of A to the K theory of B, that can always be implemented by a homomorphism. So you have a very good method of deciding when an AF algebra embeds into something. Just assuming the codomain is something reasonable, you just look for a map on K0. And also you have some amount of uniqueness of that map, that if any map with that prescribed K theory, all maps with that prescribed K theory are approximately equivalent to each other. I don't have time to really go through this. It's actually similar to this intertwining argument. It's a one-sided version of the same thing. What you do is A is this increasing union of finite dimensional algebras. You prove this in the finite dimensional case just using the structure of finite dimensional algebras as direct sums of matrices. And once you can classify maps from the finite dimensional subalgebras into B, an intertwining argument lets you line that information up and push it all the way to maps from A to B. And the corollary to this is not stated this way in Elliott's paper, but it's essentially there. And the corollary, if A and B are AF algebras, and K0 of A is isomorphic to K0 of B, then A is isomorphic to B. And what you end up showing is the AF algebras have cancellation of projections. So you can classify the morphisms from A to B, from B back to A, from A to itself, and from B to itself, and then run this argument, this two-sided intertwining argument to get the isomorphism. And this is actually how, I mean, it wasn't stated in this formalism, but this is exactly how Elliott originally got the classification of the AF algebras. And this is basically how people have been proving classification ever since. Sorry, the one last thing I wanted to point out was the, one last thing I want to mention is in the theorem like this, you have these one-sided classification results where you're just describing embeddings from one algebra into another, very often have asymmetric conditions on the domain and codomain. The domain has to be AF, the codomain has to have some substantially weaker property. And that's often the way these classification theorems go. And the morphism results often become more useful because you need substantially less conditions on the two algebras. Even in the classification theorem that I wrote at the beginning, there is a one-sided version with something a bit bigger than the Elliott invariant that, for example, doesn't require the domain to be simple and doesn't require the codomain to be nuclear. But when you run this intertwining argument, it comes back to the same class of algebras you've classified. But being able to systematically construct embeddings of not necessarily simple nuclear algebras does lead to several applications that aren't directly, you can't get directly from the statements because of this asymmetry. Okay, that's a good place to stop. So, thank you.